Okay, thank you very much for having me here. I was raised as a Catholic child, as my family is Catholic, but I wasn't really a good child in that perspective. So staying behind this bar was not an option for me when I was young. So I believe this event will make my parents proud. So when it comes to the deep learning in MRI, we have seen it a lot of different aspects of it. For example, it probably started from the data analysis doing the segmentation classification. And then after a while, we learned that we can use it for the reconstruction. So it has been widely applied in the parallel imaging as well as our QSM reconstruction. By the way, nowadays we begin to use it for the data acquisition as well. So you can design an RF pulse using deep learning or design a sequence using the deep learning. Well, when I Googled deep learning with QSM, there are already 38 papers on the topic. That's within the time period of 4 years. That's a lot of papers. And the other thing that I recognize is we love acronyms, and there are a list of them. Hope I didn't miss any of your tools. At least that should be appeared on the PubMed to be here. Before I go to the dipole deconvolution, let's talk about something else like data analysis, as we have seen some of these works in this presentation, in this conference. And they are very useful because QSM, as we all know, it is a great tool to identify and visualize deep gray matter structures. And naturally enough, we can use the deep learning to segment the volumes of different deep gray matter structures. We can use it for the identification or classification, as demonstrated in this Zhang's paper. And they are all very useful, as the contrast that we can get from the QSM is quite unique. Well, again, let's come back to the dipole deconvolution, as that will be the main topic of this presentation. And I don't think I need to explain what dipole deconvolution means, so let's just go to the next page. And if you think about how we can do this, there are two ways of doing it. The first approach is collecting multiple head orientation data sets so that you can have this well-conditioned problem. And then, in this case, we can get a gold standard result, but this is not really practical. I used to joke that this is only collectible from your graduate students who are writing the papers, and myself didn't try it. And the other one is single orientation data that we always do it for the practical purposes, but it always suffers from the streaking artifacts. When it comes to the deep learning, we know that neural nets are very successful in solving the inverse problem when there is expensive gold standard labels. For example, in parallel imaging, if you collected full K-space, you can train the network with that, with undersampled one, so that you can teach the network how to reconstruct the data sets. We can do the same thing for the QSM. We have this expensive Cosmos label and match it with a single orientation data so that we can teach the network how to do the processing of this QSM. And for inference, you can still use a single orientation, generating these Cosmos quality images. And that has been done nicely in some of the works. And this is the result, showing the upper two images are from the conventional reconstruction, showing the streaking artifacts. But QSMNet, which uses the neural net, doesn't have much streaking artifact and has the quality of the Cosmos result. A lot of people use the UNet, 3D UNet, as the deconvolution process itself is designed for the 3D. And computational-wise, it takes several seconds. That's another advantage of the deep learning reconstruction. Well, again, there are a lot of methods developed so far. If I just show you some of the interesting topics that, at least for me, not for everyone. But anyway, so this auto QSM does not require any local background removal technique, nor the mask, so that you can save the edges of the data set. People also suggested this GAN, the generative model, so that you can improve the image quality of the QSM. Also, this is quite exciting that you can use this filtered phase and you can restore the original phase by using deep learning so that you can do the QSM on your SWI data sets. Lastly, people apply the technique outside of the brain where the fat is the major challenge, and by training the network, you can generate this fat-included QSM result. Well, again, there are a lot other methods, and these four are unique in a sense, and I will come back to these papers later in the talk. Well, if you think about what I just presented so far, it feels like deep learning can be a magic tool that give you striking artifact-free images, but it turned out to be, it has a lot of issues. And the three things that I will talk about is generalization, performance comparison, and performance itself. The first one is about the generalization. So when we developed a method, the classical QSM tools can be applied for almost every application you can think of. Sometimes you face problems, but in many cases it was okay. But when it comes to the deep learning reconstruction, it was not the case, as you always bounded by your training data set. And one of the topics that we learned about is this susceptibility range. Naturally enough, QSMNet was trained for the graduate students data set who doesn't have any hemorrhage. As the result, when we had a patient with hemorrhage, the susceptibility value was underestimated because the QSMNet never saw such a large susceptibility value when it was trained for it. Well, to compensate this problem, we developed a way of doing the data augmentation using the model so that we can generate this nice linearity restored in the QSMNet plus result. Another problem is this is a bigger problem in generalization. Once your network is trained for the 1 millimeter isotropic voxel size, then it doesn't go well with other resolutions, especially if you have higher resolution. And in particular, if you have this anisotropic voxel size, it dramatically fails, despite the fact that you can do the interpolation and try to get the result, it doesn't work. People have been working on this topic of the generalization on resolution, and one of them is this XQSM, which utilizes this octave convolution that naturally mixes high frequency and low frequency together so that you can restore some of the features that may be lost in the higher resolution data sets. Another recent study is utilizing the voxel size information into your data sets, into your network, such that the network knows what kind of voxels they can reconstruct. And this particular study utilized this unsupervised learning, which doesn't really perform as much as the supervised one, but still the result shows that the network can be generalized for the resolution to a certain extent. Our approach was presented yesterday by Su-Yeon Ji. I believe this is a classic way of understanding the sampling theory and utilizing it so that we can find what was wrong with this resampling idea and compensate it based on that data processing tool. That you can still utilize the QSMNet original version of it so that you can generate the high resolution reconstruction of the data set. So you don't have to do the data augmentation, or you don't have to develop another tools. The different approach is enforcing your physics model in your reconstruction algorithm that combined with the neural network. One of those ideas is this fine approach, which is a self-transfer learning with physical model loss, so that it can be generalized for the data set that is not trained for it. So again, they are enforcing the model so that they can update the neural net weights on every data set. Another similar approach is this model QSM that utilize the neural net as a regularizer, and you still have this data consistency term based on the model. And this particular network is designed for the STI model, which includes the anisotropy information into it. Similarly, you can combine this variational network with the nonlinear dipole inversion so that you can enforce the physics on your data reconstruction. Having said that, all of them are based on certain models of QSM, either dipole or SDI. They are not really what happens in the brain. Physics in the brain is much complicated with exchange and microstructure orientation effect playing the role. So they are, to a certain extent, contains the error. So we really need to find a way to generalize the network. And also, these two things that I mentioned, the resolution and susceptibility range, is not the only factors for the generalization. So when you write the paper, make sure that it will be great to have the information about what kind of generalization your network can do so that people can compare the results. Okay, if I move to the next topic, is a bigger problem from my perspective. It's performance comparison. So now you are comparing two different networks, the one from the literature, the other one from your own. The problem of current status is the fact that we don't have any public data for the QSM. Well, my lab shares some of the data set. I believe some other people are sharing the data set as well. But largely, the reconstruction is, or the techniques developed based on the private data set. And most of the case, this private data set has different data characteristics, like resolution is different or background removal method is different. They all affect the performance of the network. So when you do the comparison, you can think about two different approaches, and this particular work will be presented by Chung-Seo Go right after this presentation. So I will not go too much of the detail, but you can think about two different ways of comparing the result. The first one is grab the neural net from the some website and just inference with your own data set. If your data set has different characteristics, then you are lucky in a sense that that neural net will underperform as compared to your data set that is trained for the same characteristics. You may believe that you can retrain the network with your own data set so that you can be fair, you can do a more fair comparison. But that still does not give you the fair comparison because neural network is not about the architecture. It is the combination of the data set and architecture. Once you retrain it, you lost the characteristic of the original data set. The far extreme of this neural network is the problem of reproducibility. Even if you train the same network with the same data set, depending on the options that you choose for your CUDA, you get the different result. The difference may be minor, but it can be statistically significant. So, and here we listed a few of the options that needs to be set to be, a certain way so that you can have some reproducibility. But this is not the whole list that guarantees you the reproducibility. So it's a big problem. So for fair comparison, I believe we need to have this public data set that everyone is using it. And also we need to share the pre-trained network with weights so that other people don't have to do the reproducibility of your data. Okay, last issue is the performance. I've been saying that deep neural net has been doing a great job in the performance-wise, but the surprise is, this challenge 2.0, no neural net won the race. There are a few of them, but almost every, category, it was conventional recon performed better than some of the neural network. Why is that the case? And the biggest surprise came like in this ISMRM, in the last ISMRM, and the paper just appeared on in Neuroimage Clinical, and I found it like 3 days ago. And this is quite shocking in a sense that they showed different reconstruction tools and different performance based on overall visual assessment, correlation with iron, correlation with age, correlation, consistency with Cosmos reference, and some disease comparison. You can see that QSMNet Plus does a good job in visually with age, with Cosmos, but does a horrible job when it comes to correlation with iron. Now, what do you mean by better performance of the neural network? Well, okay, that can be the problem with QSMNet Plus, but still, you have to think about how to measure this performance. And also, I believe this can be some of the generalization issue. They use the 7T data, and 3T was the data set for the training. But anyway, there are things that we have to think about it. Or the better question is how do you make the network better performing for a certain task or every task? So I believe we need to redefine the performance metric. Many of us utilize SSIM as the metric or some other metrics, but we need to really define some functional performance so that we can have some real evaluation of your network. Having said that, I just give you one more comments about the new techniques that coming up with the deep learning. And if you are familiar with natural image processing, there are a lot of papers talking about denoising and super resolution. And I saw 2 or 3 abstracts or posters in this conference talking about the super resolution. The question is, can we do it? Can we be safe to do it? But will it be information content that's better off by using the super resolution? What I can tell you is it may not increase the resolution itself, the true resolution itself, but at least they look great on the eyes, so they may be helpful to do it. And this is one example. On the far right, we have histology. In the middle, we have ex vivo data set. And the far left, we have in vivo data set, even at 3 Tesla. And now we can see the laminar structure of the globus pallidus, which is quite impressive to see it with our chi separation result. So with that, I want to summarize my presentation. So I believe everyone agrees with the idea of using deep learning for their study, as that has been the powerhouse for the new development in the segmentation, detection, reconstruction, and processing. But when it comes to research, the game is not over. I believe it is just started, and there are so many questions that I believe we need to address. And I believe there are the great opportunities of writing good papers and become a good contributor of the society. With that, I want to thank you and also thank my students for their hard work in the lab. Thank you very much.